So, but what you're looking at is just an awesome event, a hot air balloon event, and just beautiful. But I've watched a few videos about hot air balloons, and maybe you already know this, but basically they take regular air and heat regular air up. So kind of down, let's see, I'm going to pull up my little pointer here. Right here in the little basket, or near the little basket, or above the little basket, they have some sort of flame. So here's my little Bunsen burner. Okay, so they have some sort of flame that basically heats the air, and then the air, that warm air, is captured in here. And so the thing about warm air is, how do I say this? Warm air has a lot of kinetic energy, right? And so honestly, warm air compared to cold air is not very dense. It's sparse. So let's go ahead and take this hot air balloon. If I were to look at the particles of air in there, that's maybe how compact they are, versus the particles of air outside. That's how compact they are. So it's a density issue, okay? So the warm hot air in the balloon is less dense than the colder air outside, okay? And that's important in the next section that I need to talk about. We're overall going to talk about 3 types of stability. But in general, before we talk about the different types of the atmosphere can be these different types of stability. In general, we say a chunk of air or a parcel of air is stable if it wants to sink. A parcel of air is stable if it wants to sink. And in context of what I just said about the hot air balloon, can you see that a parcel of air will want to sink if that parcel of air is cooler than its surroundings? So this is my parcel of air, and I'm going to go ahead and say cold. And then the surroundings, I'll go ahead and just use the word cool. How's that? Okay. So if my parcel of air is cold and my air around it is cool, can you see where this parcel of air will want to sink? Okay, and we would call that parcel of air a stable parcel of air. That's it. Now, a parcel of air is said to be unstable if, in general, it is warm. Okay, we'll go ahead and say warm. And then the air around here is cool. Okay, why is it unstable? Because it wants to rise. Why does it want to rise? The same reason the hot air balloons want to rise. It's less dense, more buoyant. It wants to float. Basically, that warm air is floating in the cool air around it. So this is an example of an unstable parcel of air. So in both of these cases, can you see where my parcel of air is that circle? And in order to know if it was stable or unstable, I needed to compare that chunk of air, the temperature, to the air around it. Okay. So the types of stability we'll talk about are absolutely stable, absolute stability, sometimes I call it absolutely stable. And then the next, generally, environment, we say the atmosphere is absolutely unstable. And then conditionally stable is the third type of atmosphere. So in order to define stability, a chunk of air as being stable or unstable, we need to be able to kind of look at the air around that parcel. And back earlier we talked about something called an environmental lapse rate. Environmental lapse rate is basically, and you get them by sending up a weather balloon, basically you send up the weather balloon and it has a measuring device here to measure temperature. And it sends that temperature back, it sends the information back to all people who want it. So then you get a temperature profile of a vertical temperature profile of the air. Okay, Now, the thing about the environmental lapse rate, and I think I go with ELR. I've seen it abbreviated ELR. The thing about the environmental lapse rate is it varies. It's basically how is the temperature in the troposphere changing as you go up? Well, it varies from location to location, and for the same location, it varies over time. So weather balloons are important in giving us a gauge of what sort of what we call temperature profile, what changes is the air going on in the atmosphere as you go up in elevation with regard to temperature. Okay. Now, and I think I mentioned this before. In the troposphere, we're used to, kind of running out of room to draw this, but in the troposphere, we said that the Earth acts as kind of a mini radiator, and so as you go up in the troposphere, you get cooler and cooler temperatures. Well, that's kind of a normal temperature profile. If anywhere in the Earth's atmosphere, you basically, going up in elevation, get warmer temperatures, we call that a temperature inversion. And that creates some kind of interesting weather phenomenon. All right. So I'm going to show you an example of a chunk of air that is stable. And in order to show that, I'm going to kind of have to, one of the things I'm going to show you right off the bat is I'm going to send up a weather balloon and I'm going to come up with the ELR, the environmental lapse rate, okay? And I had to get that data. That's real-time data. So my weather balloon said basically every 1,000 meters the weather balloon went up, the air in the troposphere cooled 5 degrees. Okay, so this is what the atmosphere is about our parcel of air. 25 degrees Celsius. Okay, go up 1,000 meters, 20 degrees Celsius, go up another 1,000 meters, and it cools to 15 degrees Celsius. We got that from our weather balloon. All right, in enters our parcel of air, and I don't know if you can kind of see those 3 blobs, but that's going to be our parcel of air that's going to rise. And we talked about different lifting mechanisms. Why would a parcel of air want to rise in the first place? So it's going to rise, it's going to be forced upward. So our parcel of air starts at 25 degrees, okay? And we said that and it's going to lift, by the way, there's not enough moisture in there, there's not going to be any condensation. So it's going to lift and cool according to the dry adiabatic rate. So let me kind of cover that back up again. So do you see the chunk of air rising and expanding? And do you see that, remember we talked about the dry adiabatic rate of 10 degrees Celsius per 1,000 meters. And that's exactly what you're seeing here. It's cooling from 25 to 15. So now let's take a look at that parcel of air, which is 15 degrees Celsius now. And if we compare it to, at that same elevation, what our weather balloon said, that the temperature of the atmosphere at 1,000 meters above ground is 20 degrees Celsius. Can you see that since our parcel of air is colder than its surroundings, that basically it doesn't want to rise, okay? Basically, that parcel of air is stable, okay? Now we can go ahead and force it to ascend, and it's going to cool at another 10 degrees for rising from 1,000 meters to 2,000 meters, so it's going to cool to 5 degrees Celsius. And now here, when we compare that 5 degrees Celsius to 15 degrees Celsius, wow. Okay, the fact that this is a lot cooler, 5 degrees, than 15 degrees, it's not buoyant. It doesn't want to rise. In fact, it wants to sink. Okay, what we're describing here basically is a very stable chunk of air. It can be forced upward. Okay, in fact, that's kind of the scenario we have here by one of our lifting mechanisms. But the tendency for that parcel of air would be to fall. Why? And actually, it's specific to, and we're going to look at some different examples, if the environmental lapse rate were not 5 degrees Celsius per 1,000 meters, we might have a different outcome.